An event store is designed to be the source of truth for the state of a system. It is an append only log of events that can be used to reconstruct the state at any point in time. Now, Event Store is nothing more than just a fancy name for a database that stores events, which means we can practically use any database we want, as long as it meets all the requirements for our application. For example, we could use MongoDB, Postgres, Cassandra, or even a Kafka message broker with persistent storage, which is an event log. While Kafka was not specifically designed for event sourcing, its features and characteristics make it a suitable choice for managing event streams in event-driven architectures. Although, there's a few things to keep in mind when using Kafka. For example, we would need to ensure we have the correct ordering of events, etc. There are also specialized databases that are designed specifically for event sourcing, such as the Event Store DB. It provides a number of useful features out of the box, such as storing events in ordered streams and providing a way to filter them by type, storing their metadata, and much more. On the downside, Event Store DB is not as popular as other databases, so it might be difficult to find resources and support when needed. In this lesson, we'll learn how to implement event sourcing in our Nest.js application using MongoDB from the ground up, but just remember that you can use any database of your choice in the future. Since we're already using MongoDB for our read side, we won't even have to install any additional dependencies. Remember, the concepts and patterns we'll cover in this lesson are applicable to any data store and can be easily adapted to your needs. Alright, so let's get started. Let's first add a new Docker service to our Docker Compose file. We'll call it event-store. It's important to note here that even though we already have a MongoDB service in our Docker file, we need to add a new one that will be used specifically for storing events. Remember, this is because these two databases, which facilitate the read side and the event store side, are fundamentally different and serve different purposes. Also, as we already mentioned in a previous lesson, in a real-world application, the read side and write side services would and ideally should be deployed separately, instead of being part of the same application. In this course, we've decided to keep them together in this project for simplicity's sake, of course. This is to avoid introducing concepts that are irrelevant to what we're trying to learn, such as monorepos, code sharing, microservices, message brokers, etc. If you're interested and want to learn more about these topics, find out more in our dedicated microservices course extension. Back to our Docker Compose file here, what's also different about this service that we just added is that we're using a different port, 27018, because otherwise we'd run into conflicts. And we're also using a different command to start the MongoDB server. We're passing the REPL set flag to enable replication and specify the name of the replica set, VF Event Store REPL set. This is required as we'll be using MongoDB change streams to listen for changes in the event store, and they only work with replica sets. We're also mounting a new file called Event Store Mongo init with the Docker entry point initdb directory. This file will be executed when the container is started and will be used to initialize the database. Let's go ahead and create this file inside of the new scripts directory. We don't need to pass any configuration here since we'll only have a single node in the replica set. With this service in place, we can now run docker compose up-d to start the event store. Great! Now that we have our event store up and running, let's navigate to the core directory and create a new file there called core constants with the following content. We'll use this constant to register a separate MongoDB connection for the event store. The reason we're doing this is because we want to maintain two different MongoDB connections in our application, one for the read side and one for the event store. But to achieve that, we need to give them different namespaces. Next, let's head over to the core module file and import the Mongoose module. Note that we're passing the connection name option here to give this connection a different namespace. And we're also setting the direct connection option to true, as we need to connect to local replica sets. Without this option enabled, you may run into errors when running your event store inside of a Docker container. Also, since in this course we won't be implementing an in-memory event store, we just imported the Mongoose module in the static configuration object of the core module. If you want to practice everything you learned in the hexagonal architecture section, you can try to implement a swappable in-memory event store on your own. Great, moving on. Now that we have our event store connection set up, let's create a new module called Shared that will contain all the shared code for our application. You may be asking yourself, why aren't we going to use the existing common folder for this purpose? Well, the reason is that this is a common pattern in Nest.js applications, because the common directory should be meant for containing interfaces, abstract classes, commonly used pipes, guards, interceptors, and basically any components that can be shared across multiple modules and at the same time, all of which do not belong to any specific module. Whereas shared, on the other hand, will mostly contain components registered and exported from a dedicated shared module that we're going to create in just a moment. While these concepts may seem similar, they're actually quite different. However, if you find this confusing, you can always use the common directory for both purposes, as long as you're consistent with your naming conventions. Let's head over to our terminal and call nestgmo shared. Once the module is created, let's open up the shared directory, and inside of this folder, let's create two new directories, one being domain and the other called infrastructure. We'll first focus on the infrastructure directory. Let's open it up, and in order to have everything nicely organized, let's create a new directory called Event Store inside of it. This folder will contain all the code related to the Event Store implementation, including the Event Store class itself. So let's stop here for a brief moment and think about what we need to implement first. We need to declare an event Mongo schema that will represent the events stored in the database. We'll also need serializers and deserializers to convert events to and from JSON. To connect our in-memory events stream to the event store, we'll need to implement a publisher class that will hook up to the CQRS module. And finally, we'll need a class that will be responsible for storing and retrieving events from the database, the Mongo event store itself. Perfect. Now that our game plan is all clear, let's actually start implementing everything. Let's first create a new file called event schema inside of the schemas folder and add the following content. This is a pretty straightforward schema definition, but let's break it down to make sure things become even more clear. First, we're using the schema decorator to specify that we want to enable the created@at timestamp for this schema, which means that every time a new event is created, this created@at field will be automatically populated with the current date and time. Our class will contain the following properties: stream ID, the ID of the stream to which the event belongs. This usually equals the aggregate ID, which can be prefixed with the aggregate type as well. Type, the type of the event. Position, the position of the event in this stream. And data, which is the event payload. Below, we're also creating a unique index on the stream ID and position fields. This is essential as we want to make sure we'll never have two events with the same position in the same stream, which could occur if we had multiple operations happening at the same time on the same aggregate and in parallel. By creating a unique index, we're making sure that the database will throw an error if we try to insert an event in the same position, consequently preventing us from corrupting our event stream and leaving us with a consistent state. Now, this position will also represent the version of the aggregate, so we'll need to make sure that we always increment it by 1 when we append a new event to the stream. We'll see how to do that in just a moment. So with our schema in place, let's navigate to the domain folder, and here, let's create a new file called version.ts inside of the value objects directory. Version will be a simple primitive, a number, but by wrapping it in a value object, we're adding some additional semantics to it, making it more explicit and self-explanatory. So inside of the version file, let's add the following content. And that's it. Next, let's create a new aggregate root.ts file in the domain folder and add the following content. Alright, so what we have here is a base class for our aggregate roots. It extends the aggregate root class provided by the Nest.js CQRS package and adds a version property to it. This property is private and can only be accessed via the getter and updated through a private setVersion method. We're also setting the initial version to 0. Lastly, let's create a new folder called Interfaces, and inside of this folder, we'll create the serializable event TS file with the following content. Now let's break it down line by line, starting from the bottom to the top. We're defining the serializable event interface that will represent an event that can be stored in the event store. It will contain the same set of properties as our Mongoose event schema: stream ID, type, position, and data. However, the data property will be serialized version of the event. We'll see how to serialize the event payload in just a moment. Above it, we're defining the serialized event payload type that will be used to infer the serialized type of a given event payload. It's a recursive type that will iterate over all of the properties, and if a property has a toJSON method, it will infer the return type of that method as the serialized type. Long story short, serializable event describes the shape of the event that can be stored in the event store. We need to serialize the event payload before storing it in the database to auto-unwrap any value objects and convert them to their corresponding primitives. Back to our infrastructure folder, let's create a new directory called serializers, and inside of this folder, we'll create the event serializer TS file with the following content. This class here will be responsible for serializing domain event instances into a format that can be stored in the event store. It provides a single serialized method that accepts two arguments: the event instance and the aggregate root instance that dispatch the event. Inside the method body, we're extracting the event type and aggregate ID, and then we're returning a serialized event object. To determine the position of the event in the stream, we're simply incrementing the current version of the aggregate by 1. Also, we're using the toJSON method, which is missing, to serialize the event payload, so let's go ahead and create that method now. What this method does is that it iterates over all the properties of the event, and if a property has a toJSON method, it will call it and return the result. Otherwise, it will return the original value. While it looks fairly complicated, it's actually pretty simple. Excellent. Now that we have our event serializer in place, let's create a new file called Mongo Event Store and add the following content. This class here will be responsible for persisting events in the event store. It provides a single persist method that accepts either a single event or an array of events and then saves them to the database. We're using the insert many method provided by Mongoose to insert multiple documents at once. You can see there's also a try-catch block to handle any errors that might have occurred during the insertion, but for now, it only aborts the transaction. So in the code here, we're checking if the error code is equal to 11,000. This is the error code that MongoDB returns when a unique constraint is violated. If that's the case, we're logging an error message and printing the error message out to the console. We'll use this error code to detect for stale aggregates. Basically, this is the scenario that we described earlier, where there can be multiple parallel operations on the same aggregate, but we want to ensure that only one operation can succeed. Perfect. Now that we have our event store in place, the only thing that's left is to connect our newly created event store to the event bus. So let's go ahead and do that now. Let's start by creating a new publishers folder, and inside of this folder, we'll create the event store publisher TS file with the following content. This class here implements the iEventPublisher interface provided by Nest.js CQRS. This interface enforces us to define the publish method, which accepts two arguments: the event instance and the aggregate root instance that dispatched the event. Inside the method body, we are serializing the event with the use of the event serializer we created earlier, and then we're persisting it in the event store. There's also the onApplicationBootstrap method that will be called by Nest.js when the application is bootstrapped. Inside of this method, we're setting the eventBus.publisher property to this, which means that the event bus will use our event store publisher to publish events. While this is all we need for our application, let's also add a new publishAll method that can accept an array of events and then publish them all at once. We won't need this in our current project, but it might come in handy in your future applications. The only difference here, compared to the regular publish method, is that we're updating the position of the event in the stream. We're doing that by adding the current version of the aggregate to the index of the event in the array and then incrementing it by 1. Note that this is very important to ensure that the events in the array are stored in the correct order. Excellent. Finally, let's wire everything up by creating a new shared infrastructure module file with the following content. Here, we're just registering all the providers we created earlier. Finally, let's import the shared infrastructure module into our shared module and then re-export it. And last but not least, let's import the shared module into the alarms infrastructure module and again, re-export it, and then we're all done. Great. Before we test everything out, there's still a few things we need to change in our alarms module to integrate it with the event store that we just created. First, let's navigate to the domain folder and open up the alarm.ts class and make it extend versioned aggregate root from our shared domain. Since we're now extending the versioned aggregate root class, we need to make sure that we're calling the super method in our constructor. Next, let's head over to the alarm factory, and after creating a new alarm instance, let's call the apply method of the aggregate, passing in the alarm created event instance. You can see that we're also setting the skip handler option to true in order to skip the execution of the local in aggregate event handler. Don't worry, we'll talk more about this in the next chapter. Finally, let's navigate to the create alarm command handler and let's update its dependencies first. We're not going to need the event bus nor create alarm repository providers, so let's go ahead and remove them. Instead, we're going to need the event publisher, so let's go ahead and inject that here. Inside of the execute method here, let's remove the saving logic and event bus publish call, and instead, let's use the event publisher to merge the publisher context with the alarm aggregate instance. Now, this one's important. Merging the publisher context with the aggregate instance will allow us to use the apply method of the aggregate to apply the event to the aggregate and then commit the changes to the event store. This is a crucial step, as otherwise, the event would never reach the event store. So, with all of that, let's save our changes and test everything out. Let's open up our terminals and make sure that our application has bootstrapped successfully. If so, let's switch to the other terminal window and let's create a new alarm by sending a post request to the alarms endpoint. Once again, we're using the JSON PP tool to format the output, but you can omit it if you need to. Great, so it seems everything's working. Let's switch to the other terminal window and let's check the logs. As we can see here, there are no errors. Our event was successfully persisted into the event store. However, there's no sign of the alarm created event in the logs, meaning the alarm created event handler was not executed. Also, if we try to fetch the alarms, we'll see that our newly created alarm is not there. But why? Well, while we did publish the event to the event store, we didn't yet set up watchers that would listen for new events inserted into the MongoDB collection and execute the corresponding handlers. But not to worry, we'll do all of that in the next lesson. If you've been following along so far, great job, keep it up. If you're seeing any errors here, make sure you didn't miss any of the code snippets or files that we added throughout this lesson. All of the code can be found below the course video as always.